Okay, so this is a continuation of the last lecture. We continue with the differential amplifier with a PMOS current source load, and we look at the common mode gain and the gain with arbitrary inputs, and also look at CMRR. So now we say, well, this is a differential amplifier. What happens if we apply the say equal AC inputs at both the terminals, the so-called common mode input? So we have a DC, on top of it we have an AC, and the AC is equal. Of course, now the circuit is symmetric, so we can conclude that VO1 will be equal to VO2. Now we want to find an expression for VO1 equal to VO2. So we draw the small signal circuit. So this is a small signal circuit. Now what I have done is, instead of one RO5 at the bottom, I have divided that RO5 into two parallel resistances of value 2 RO5. So 2 RO5 in parallel with 2 RO5. And now if you look at this configuration, everything, and if we cut this in the middle, then everything on the left is the same as everything on the right. Everything is identical, and because it is identical, no current will flow in this wire from the left to the right, because there is complete symmetry, and complete symmetry implies that we can cut the circuit in the middle with no effect on the circuit behavior at all. And this, so the ability to cut it in the middle allows us to analyze only half of this circuit, either the left half or the right half. Anyway, they are identical. All right, and if you look at only the left half, then this is a circuit of a common source amplifier with source degeneration. All right, so we had RDRS earlier, now we have RO3, RO5. And this circuit we have analyzed earlier, so we will not analyze it again. We will simply write the expression. So this we did in lecture 14, slide 6. So the voltage gain of the one half of the circuit is VO1 over Vin. So Vin is Vc is equal to minus GM1 RO1 RO3 etc etc etc, and that is equal to approximately minus RO3 by 2 RO5 if GM1 RO1 is much greater than 1. So we had seen this before. The voltage gain of a amplifier with source degeneration is small. If ROs are equal, the gain is only minus half, and so that is the voltage gain of this circuit. It is interesting to recognize that in the approximate expression, RO1 is not appearing. This is dependent only on RO3 and RO5. Now, why would that be? The reason is that when we make this assumption that GM1 RO1 is much greater than 1, and if you look at this circuit, then what is happening is there are two paths for the current to flow in M1, either through the current's dependent source or through RO1. And by making the assumption that GM1 RO1 is much greater than 1, basically we are saying that most of the current flows through the current source and very little current flows through RO1, and so we can simply ignore RO1, and then the voltage gain will depend only on RO3 and RO5. In other words, if we were to assume that RO1 is infinite, that would basically we are saying that RO1 is much greater than 1 over GM1. So we are making that tend to infinity. So for example, if we were to make RO1 infinite in this expression, then this is what we'll get, and that will simplify to the same minus RO3 over 2 RO5. All right, so this is the common mode gain of our differential amplifier, and it is small, and that is good, because we don't want our differential amplifier to have a common mode gain. It is about, if ROs are equal, it is minus half, which is a good thing. All right, so let's write both the gains of the differential amplifier. The differential mode gain, which we had derived last time, is minus GM1 RO1 parallel RO3. If this is VO1, it is VO2, then it is plus. The plus minus sign is not really relevant. The common mode gain is minus because both VO1 and VO2 will be negative with respect to the inputs. You must have heard of CMRR, common mode rejection ratio, which is defined as the ratios of the differential mode gain to the common mode gain. The mod of it, CMRR is generally the magnitude of this ratio. So we can write this as basically this divided by that mod. So that is the expression. Now you also probably know that we always want the CMRR of a differential amplifier to be large. So you want large AD and small AC. Why is that? You think in your head, all right, or maybe write it down somewhere. I assume that you know the answer. So here are a couple of answers. So the purpose of a differential amplifier is to achieve this equation, right? We want the output to be equal to some voltage gain times the difference between the two inputs. So now suppose both the inputs, so these are AC inputs. So if both the inputs have the same value, they are a common mode input, then of course we want the output to be 0. Ideally, we want the AC output to be 0 when a common mode AC input is applied. So ideally we want AC to be 0 because why? Because the differential amplifier. We want it to amplify only differences, not common mode signals. So the equivalent of the balance is that, so if this part of the balance is rigid and it has it doesn't stress at all or stretch at all, then if we increase the weights equally in both the pans, then the pans don't move at all. So that is an ideal balance. Now if there was a spring, they'll both move and there'll be a slight displacement, which is a non-ideality. Similarly, in a differential amplifier, we don't want the output voltages to change when the inputs change equally. We want it to change only when a differential input is applied. All right, so the fact that there is a common mode gain is actually a non-ideality of the differential amplifier. An ideal differential amplifier will have a 0 common mode gain. All right, so a practical reason of where a high common mode gain is important, right? A practical application. So a very common application of operational amplifiers with two inputs and a differential gain is in a lot of biomedical applications. One common one is the electrocardiogram. So in a simple electrocardiogram, ECG, and actually ECG has 8 electrodes, but let us think of only 2 electrodes. And so what we do is we'll put the 2 electrodes on the chest at different parts of the chest, and these ECG signal will be picked up by these electrodes, and that will be sent to an amplifier to amplify, and the difference will be amplified. Now what happens is the electrodes, the body, the cables that carry the signal from the body to the electronics all pick up the 50 hertz from the air. Right? So we have these wires running around wherever the patient is. Typically the patient is inside a room, a hospital room or a clinic or even a home. There are always our power lines, power wires all over the room, inside, concealed or otherwise, and all power lines have electromagnetic fields around them, and those electromagnetic fields are picked up by the body. The body acts as an antenna. The cables that carry the signal from the chest to the electronics act as antennas, and they pick up this 50 hertz, the 60 hertz, 50 hertz, 50 here, 60 in the US, I never remember, and it's 50 in India. So the 50 hertz power signal is picked up by the body as well as by the cables. And the magnitude of these signals that are picked up, the wire of course has, the power lines of course have 220 volts, but by the time the electromagnetic field around the wires and by the time it's picked up, it can be anywhere between 1 and 10 volts. So that is a 1 and 10 volt of 50 hertz picked up, that reaches the amplifier, the differential amplifier, which is the first thing that is the electrode encounter. The ECG signal on the other hand is a few millivolts. The ECG signal is a differential mode signal. The 50 hertz signal is a common mode signal. We don't want the common mode signal to be amplified. We want the differential mode signal to be amplified. So you have a 10 millivolt ECG, let's say a 1 volt common mode signal. At the output of the differential amplifier, this 1 volt must become small and this 10 millivolt must become large. And we want this 10 millivolt to be larger at the output of the differential amplifier than the 1 volt, so that the 1 volt doesn't interfere anymore. So you want the common mode gain to be very small and the differential mode gain to be very large. So here is a very practical application which is used. I mean, this principle of a high CMRR is critical in designing differential amplifiers for ECG detection. All right. So we say, okay, we want to make our common mode gain small, and therefore by doing that we want the CMRR to be large. So we ask ourselves, okay, we've designed a differential amplifier, it is giving some differential mode gain, it is giving some common mode gain, and we saw the expressions already. Now suppose we want to reduce the common mode gain, or in other words we want to increase the CMRR. Generally a CMRR specification is given to the circuit designer. So let's say our design does not meet the CMRR specification. So we say, okay, I want to reduce my common mode gain. How do I do it? So how do we do it? We look at the expression of the common mode gain. So we just derived the expression. The approximate expression is RO3 over 2 RO5. And if we write it, the ROs in terms of lambda IDs, then RO3 is 1 over lambda 3 ID3. RO5 is 1 over lambda 5. This is a tail current. This is a tail transistor. So its current is double the current in the two branches of the differential amplifier. So this is twice ID3. There's a 2 here. So 2's cancel, ID3's cancel. So we'll get lambda 5 by lambda 3. So we say if we want to reduce AC, we must make RO5 large. Alright, RO3 is going to affect the differential mode gain. So we don't want to mess with RO3. Whatever it is, we'll keep it. RO5 has no effect on the differential mode gain. So we play around with RO5. So we say to make AC small, we must make RO5 large. What is RO5? The RO of the tail transistor. And how do we make RO5 large? We either make the length of M5 large or we put a cascode tail current source. Alright, so one of these two are done to make the common mode gain smaller. So this is an important design principle. As you will later see, when you are designing a differential amplifier, first one designs for the differential mode gain, the input common mode range, etc., etc. Later, once all that is complete, if the CMRR is not met, then one adjusts the length of the tail transistor. Alright, because that is an independent control as opposed to everything else. And if the CMRR is met, you don't worry about the tail transistor. Okay. Alright, now let us ask one more question. Suppose I am given an amplifier and I am given the differential mode gain and the common mode gain, and I am told that the two inputs applied to the differential amplifier are AC inputs are 3 cos omega t millivolts and 10 cos omega t millivolts. And the question we are asked is how much is the output voltage? Any one, VO1 or VO2, what is the output voltage? I think you've done this before, so, but if you have, well, if you have done it or not done it, just pause and do it now, just for the sake of completeness. So these are to any random input supplied, and it's a simple principle of mathematics that two independent variables can always be written as a linear combination of two other independent variables. So what we do is we convert V in 1 and V in 2 to arbitrary inputs into a differential mode input and a common mode input. The differential mode input is simply the difference between the two inputs. The common mode is the average of the two inputs. And once we have defined these two, then we write the output as a superposition of the differential mode output and the common mode output. So VO1 is equal to the differential mode gain times the differential mode input plus the common mode gain times the common mode input. Alright, so this is how you find the output of a differential amplifier for arbitrary input voltages. Because I want to discuss this effect of differential mode and common mode gains on an amplifier that has negative feedback. This doesn't get discussed commonly, and I think it's an important thing to kind of understand and learn about. So let us say we have a unity gain buffer circuit, right? And an amplifier where the output is connected to the negative input of the operational amplifier, and the input is applied to the positive terminal of the operational amplifier. And as you know, in an ideal case, VO is equal to V in. But now let us consider a case where neither the differential mode gain is infinite nor the common mode gain is 0. All right, and let's see what happens. So we say, okay, let us say the input voltage changes from 1 volt to 2 volt. All right, so when the input voltage changes, of course, what will happen is because of feedback, both the positive and negative input terminals of the op amp or the differential amplifier will change from 1 volt to 2 volts. So this is a change in the common mode input voltage because both the inputs have changed from 1 volt to 2 volt. So there will be a common mode gain applicable in this situation. So let us quantify this. So we say, okay, so we have two input terminals as we just saw. V in 1 and V in 2 are the two terminals of the differential amplifier, and the differential mode voltage is VD, common mode is VC. So we can write the output as AD into V plus minus V minus plus AC into V plus plus V minus by 2, where V plus and V minus are V in 1 and V in 2. So we say for our unity gain buffer, the output terminal is connected to the negative input terminal. So V minus is equal to VO, and the input in the unity gain buffer is applied to the positive input terminal. So V plus is equal to V in. So we substitute for V minus VO here and V plus V in here. So we get an equation in VO and V in, and we solve for VO in terms of V in. Then we get this equation. So VO equal to AD plus AC by 2 divided by AD minus AC by 2 plus 1 into V in. Now suppose AC is 0, the common mode gain is 0, then we'll get AD over AD plus 1 into V in, which you may have seen before. And then if AD is infinite, then AD over AD plus 1 is simply 1, and we get the ideal case of VO equal to V in. But if AD is not infinite and if AC is not 0, then this is the equation. So let's consider two cases. So let's say AD is 100 and AC is 0. So I want to see the effect only of a finite differential mode gain and no common mode gain. So we get AD over AD plus 1. So 100 by 100 plus 1, and let us say V in is 1 volt. So 100 by 100, 101 into 1. So VO will be 0.99 into V in. So this 0.99 instead of 1 is called as a finite gain error of the unity gain buffer or of the operational amplifier. Now suppose we have AD equal to 100 and AC equal to 10. Okay, that's not a very good CMRR, but that is the point of this example. So if this is 100 and this is 10, so we'll get 105 divided by 101 minus 5, so 96. So 105 divided by 96. So that turns out to be 1.09. All right, so the voltage gain, which ideally should be 1, has become 1.09. There is a 9% error in the output because the common mode gain is not small enough. All right, so the common mode gain 9% is a significant amount for a large number of applications. And so this kind of exemplifies why we want to make the common mode gain as small as possible. All right. Okay, so the next lecture we'll talk about differential amplifiers with a current mirror load.